Great. Thank you. And this is actually my first ever time at Multi-Core World, so thank you very much for the invitation. It's delightful to be here. My name's Simon McIntosh-Smith. I'm a professor at the University of Bristol. I'm director of the Bristol Centre for Supercomputing, and I am a computer architecture geek. Really is my first love and my background, and actually that's what I started off doing. So I'm a computer scientist by training. I spent 15 years in industry when I graduated, designing microprocessors. I was a chip designer in Bristol, and that's how I've ended up in Bristol. I went initially to work for a company called InMOS, if you've been around in high-performance computing for a very, very long time. You remember InMOS and the things like transputers and Occam. This is really a 1980s vintage of computer architecture, so that didn't used to feel like a long time ago, but it really is now. And after InMOS, I worked for a couple of startup companies doing very parallel processes. I worked for a company called Pixel Fusion. We were doing fully programmable graphics in the 1990s. This was when most GPUs, if you were into gaming at that time, you'd have an NVIDIA Riva 128. And these were ASICs. These were fixed function graphics, right? They were not programmable in any way. They would do Direct3D, DirectX, OpenGL, basically in hardware. And we were designing a very, very parallel chip, 1,500 8-bit ALUs for doing pixels in a fully programmable way. And actually from that company, we created ClearSpeed. And some of you may remember this. This is now more like 20 years ago. In fact, Tsubame 1, which is the Tokyo Tech series of supercomputers, used the ClearSpeed hardware to get into the top 10 of the top 500. So that's my background. And then in 2009, I made the jump back into academia, where I've been doing lots of computer architecture related research, which somehow has led to me building and running supercomputers. But today we're going to talk about what's driving computer architecture development. And obviously it's AI, right? We all know this. Dan did a brilliant talk yesterday showing how the AI market's ballooning. There are lots of these sorts of charts you can find on the internet. This is a pretty good one showing the predicted growth of AI, both sort of for cloud and on-prem. And obviously a big chunk of this is cloud, but a big chunk is on-prem too, which is quite interesting. And of course, who knows what's really going to happen? And maybe this will flatten out, or we just don't know. But if you kind of look at where we are today, we've had pretty fast growth the last couple of years. Even for the next few years, if it does anything like this, this is a pretty huge, 30% year-on-year growth is massive. Everything else is tiny by comparison. So this is the juggernaut that's driving most development in computer hardware right now. It just is, and there's nothing we can do about it. So that's one of the first things we've got to take on board. So AI is basically driving lots of things, including computer architecture. There are other things, so we have to care about things like performance, and actually that a lot of people have realized for a while now, performance is basically performance per watt. Almost every kind of operating environment is limited by power, whether it's a supercomputer with hundreds of megawatts or your mobile phone with just a few watts. Ultimately, you've got a limited amount of power and you've got to give as much performance as you can. So performance is largely being driven today by performance per watt, by energy efficiency, which is also related to, well, with things like AI really, really growing, we're using more and more power to deliver AI. And actually, AI isn't the only thing doing this, right? Society is increasingly digital, and even without AI, we'd be seeing pretty big growth in data centers and how much power they're using. So we can't blame all of this on AI, but we are putting more and more power into the digital underpinnings of society, and the more efficient we can make that, the better. Some of that's to do with cost. This is cost per kilowatt hour in US dollars, and you can see some places are much cheaper to get your electricity than others. So at the top, we've got things like Ireland, and let's see, they're sort of 45, 47 cents per kilowatt hour. UK's up near the top, so I pay roughly 40 cents per kilowatt hour. It's come down slightly, it's about 25 pence a kilowatt hour now. But there are some places, in fact, this chart keeps going off the bottom, where it gets a lot cheaper. I think it's relatively good here in New Zealand, isn't it? You get pretty good power. So that has a big impact. I'm running a big supercomputer, so I care about this. I care about how much power is costing. So why do I care about any of this? So I started off designing processors, and now I build and run giant supercomputers. So giant to me, I know Andrew would say, this is not giant compared to Microsoft. Giant to me, 5 megawatts. I'm building something called Isambard AI at the moment. It's a huge investment from the UK government, over £300 million to buy and run an AI supercomputer for the UK. We don't have anything like this in the UK at the moment. This is going to be much bigger. It's a huge leap beyond anything we've built in the UK so far. It's about 5,500 NVIDIA Grace Hopper GPUs. That gives us about 21 exaflops of 8-bit, which for the AI stuff we're doing is the most important. It's about 250 petaflops 64-bit, which doesn't really matter. It'll be the fastest supercomputer in the UK when it's fully installed later this year. One of the most disruptive and innovative things about this is we're doing it very, very quickly. That's not something we necessarily have a good track record of doing, certainly in academia, doing things quickly, because these things are big and complicated. But we've found ways of doing this using things like modular data centers so that we can do it very quickly. We've gone from basically a first conversation about the idea to having the system built and deployed in a new site in about 18 months. Normally that would take us 4 to 5 years, and we'd be pretty happy if we did it in that time. So this is astonishingly quickly. The first part of this is already here. So we've got a little system that's already in. So this is actually the real system, 168 Grace Hoppers. And last May, when this part arrived, this came in at number 2 on the Green 500. We were very pleased about that. It's only one rack of equipment, 168 GPUs, but it ranked 128 in the top 500. So that's how powerful these things are, how dense they've become. The full system will be 5 megawatts, which at UK energy price is about £1 million a month. So that's quite a lot of money on power. That's why the price of power and energy efficiency really matters. Now, I've said we're building it very quickly, so rather than just telling you, I'm going to show you. So this is a time lapse. I'm famous for these time lapses. This is a new one. So this is a university car park. This is one of the benefits of COVID, is we all got used to working from home. So we've got lots of car parks that aren't anything like as busy as they used to be. So why don't we put them to better use, right? So we've decided to turn one of the university car parks into a data center, and to do it very, very quickly. Now, there's already something in this picture, and that's actually I said we've already got one of the systems in, so then that's where it is. So that little compound in the corner, that little wooden fenced area, that's the first modular data center we built. There's something that looks like a shipping container. It's purpose-built as a data center. It's not a shipping container, but it's that kind of dimension. It's about 40 feet long. And that's a 1 megawatt facility, and we did that in 4 months. So I can show you another time lapse. We haven't got time now. Where we built that from breaking ground to the whole thing built with the system inside, doing its top 500 run in 4 months from start to finish. So that was our kind of practice run, if you like. And now, since the start of June last year, so we've got a little counter at the bottom, you can see what's involved in building a new site for a 5 megawatt AI supercomputer. Now, the nice thing about modular data centers, you don't need to build buildings. You're basically building a big concrete pad, something. Now, these systems are very heavy. So initially we thought we might have to do quite shallow foundations, and you see we've actually got really deep concrete, because it turns out these things are hundreds of tons. By the time you've got all of the cooling, all of the water, the systems themselves are very, very dense. So it's all very, very heavy. So quite deep foundations. The actual delivery of the modular data center happens in 48 hours. So that's it all in. That's the modular data center there now. Manufactured offsite in the Netherlands, driven and sailed across the channel. This is over Christmas and New Year, it got a bit quieter. The structure in the middle is actually a security cage. It's just a fence. And now what we're building in the front, this is where all the transformers go. So there'll be 5 megawatts of transformers, and the water treatment plant will go inside this building, which will get the skin on in the next few weeks. So the actual IT equipment starts to turn up at the end of next week. So this was Friday. and so things are happening incredibly quickly. It's been quite exciting. Is a very British way of putting it. I think the New Zealanders will kind of appreciate what I mean. Here's a slightly different angle. This was actually the week of supercomputing. Those of you who were in the US, in Atlanta, you can see part of the system turning up on. It came on 6 trucks. They got craned in. It was snowing. That hardly ever happens in Bristol. So we didn't have that on our RISC register, but they managed to do it in just 2 days. And so the whole thing was craned in very quickly. So this is a really interesting way of building supercomputers with modular data centers. You can do it very fast. The first system's already doing real science. This AI stuff is really quite interesting. So I started off as a skeptic, but I'm seeing now the real science that people are doing on this, and it is quite incredible. This really exciting stuff happening. We've got several different projects involved in drug discovery, people working on vaccines for Alzheimer's. In fact, one of them is a vaccine for dementia, full stop. And these people think they've got a real chance of doing this in the next 10 years or so. So imagine how that could affect all of us, right? If you could be vaccinated against dementia within the next few years of our lives. This is the sort of thing that people are really using these machines for. So really exciting stuff. One of these projects is people using AlphaFold and OpenFold, which is sort of the open version of that, looking at heart health and how inflammation causes part of what goes wrong when you have heart disease. So this is fantastic stuff that these machines are genuinely being used for, not just commercial stuff, but stuff that's hopefully going to affect all of us and make our lives better. So it's good in a way that AI is driving computer architecture. And the reason it's happening, we've already said, partly it's the biggest market. Something else, though, when you look at AI, is it is still changing very rapidly, right? So if you said today, could you turn what people are doing right now into an ASIC? You could, but in a year, it might all change, and that would be completely the wrong thing to do. So it's still too early to put too much of this into sort of fixed function, highly optimized ASICs. That's why I think GPUs and things similar to GPUs are going to stay the dominant way of doing this, at least for the next few years. Might not always stay that way, but I think certainly for the next few years it will. Important characteristics have emerged from the way people are doing AI now. So, for example, sort of general matrix multipliers, sort of small matrix multipliers, and actually that's maybe slightly more generalized to small BLAS operations. So sometimes it's a matrix vector, a little bit of vector, so small kind of linear algebra type operations. Reduced precision. We've seen a lot of people mention that in the last few days. You don't need 64-bit for most of this. In fact, over the last years, it's gone 32-bit, 16-bit. We've heard people talking about 8-bit, even lower, so lower precision. Sparsity, so a lot of what goes on inside the networks that people are using results in sparse data sets. And actually inside architectures now, there's designs that are learning how to not even move the zeros, just use the indices to pull all the non-zeros, pack them into a dense operation, do small dense operations, and that saves a lot of data movement and a lot of unnecessary operations as well. So sparsity's ended up being a big deal, but maybe that had never really come out and driven things from an HPC point of view, but in AI it really does. The way we're seeing the architectures evolve to meet those sort of needs, we're seeing matrix accelerators show up, and often these show up in GPUs first because they've really been on the sort of forefront of trying to meet the needs for AI, for things like NVIDIA's TensorCores, but also ARM's got SME, there's other things that have gone into x86. It's not just about GPUs. These little accelerators for doing the matrix operations, those are often now getting very good at dealing with sparse data in ways that we haven't had before. Data prefetching's become more and more important to get good at moving data around in sort of AI styles. Memory bandwidth is always an issue, and maybe it is always an issue. Most HPC codes tend to be bandwidth limited rather than flop or compute limited, and that often ends up the case for AI as well. And one of the sort of slightly more general trends that's come out in this space is especially the hyperscalers designing architectures more specifically for this kind of area. And you've seen Google do their TPU. Most of the hyperscalers have their own sort of similar, more application-specific processor they've developed for this space. There are a few more independent ones like the GraphCores, etc., of the world as well. Digging into each one of those in a little bit more detail, the GPUs do tend to be on the bleeding edge of that floating point capability. This is a picture from the Hopper GPU, support for all these different 32-bit, 16-bit, different sorts of 8-bit floating point. That's all specifically kind of optimized for AI. And then the TensorCore fits in on the right-hand side where you can suck in different sorts of data in different precisions, do your matrix multiplies, accumulate at whatever precision is most appropriate, do a few other little bits of operation, and then sort of spit out different sorts of precision as well. And the very latest GPUs, the Blackwell from NVIDIA, adding even more different formats. There's a 6-bit floating point and a 4-bit floating point. So we can't go lots more than that, obviously, but there's still innovation going on in that space, just in the basics of a floating point. So often it's the GPU that's at the vanguard, but the CPUs can do that too, right? There's nothing stopping you doing some of this really clever stuff in a CPU. So ARM's got something called the Scalable Matrix Extension, and in fact, the very latest, I've got this is a new M4-based Apple MacBook, and that has SME in it. So I've got that in the laptop that's running this PowerPoint. I imagine it's not using it very much right now, but it's got it in there. The latest Intel CPUs have got something similar. IBM's had something like this since Power 10. In earlier generations of Apple, if you've got something, Apple actually had their own flavor. So it wasn't an Apple sort of official SME, but they had something called AMX, which is sort of Apple's slightly different version. And that all does the sort of level 2, level 3 BLAS, vector matrix type operation. And maybe for small operations, rather than offloading from a CPU to a separate GPU, you could just quickly do it right there in the CPU. Maybe that's quicker. So the CPUs can do some of this stuff too. And in fact, CPUs, they're kind of really overlooked now, aren't they, compared to GPUs? We're used to AI, it's all about NVIDIA and maybe AMD. But actually, CPUs have been improving at a remarkable rate. So I said I'm an architecture geek. I'm very proud of that. I love these sorts of block diagrams. So this is a microarchitecture block diagram of the ARM-based CPU in this laptop. So in this M4-based laptop. So this is actually designed by Apple. And the important bit is it's very wide. So you see all of these blocks are very, very wide. This bit in the middle, this is how many different instructions can be fetched and decoded at once. There's 10. So each core in my laptop right now is every cycle fetching and decoding up to 10 instructions every single cycle. The first Isambard supercomputer I built in 2018 had very advanced processors, and they could do 4 instructions every cycle. And at that time, state-of-the-art was about 4 or 5. So we've gone from 4 or 5 instructions a cycle up to 10 since 2017, 2018. That's remarkable. So now up to 10, this is 10-way superscalar is how you describe this. Other numbers are a bit too small. In the middle here, this is a thing called the reorder buffer. That says it's got 918 entries. What does that mean? It means in one core, we could have over 900 instructions in flight at any one time. So in this one core, in my little laptop, battery-powered laptop, one core can have over 900 instructions working at once. And this laptop has 16 cores in it. 12 of them are this performance type, and then 4 are slightly simpler, more efficient ones. So it could be doing nearly 1,000 instructions in one core times 12 in my laptop. That's how fast CPUs have been progressing, and it's not stopping, right? So there'll be a 12-way superscalar, 14, 16, it'll keep going up. So maybe in another 7, 8 years, we'll be at 20-way superscalar. CPUs are not stopping, they're still improving, they're still becoming more and more sophisticated. Right down at the bottom is where all the loads and stores happen. It could do 3 loads and 2 stores every cycle. So of those 10 instructions, half of them could be loads and stores. These are amazing machines now. As a computer architecture geek, I'm astonished at what's possible. So don't rule out the CPUs. They can do really cool stuff too. I mentioned the TensorCores got clever with sparsity. This is actually another NVIDIA diagram, and it sort of shows how the weights that you suck in can have ended up sparse because of other things that have happened when we've been processing the neural networks, but they can get squeezed, packed, if you like, so that we only then do operations on dense data as they actually flow through the execution units inside the tensor cores. And this is now a common approach that most architectures are doing similar things, and it does make quite a big difference if you do this. Otherwise, you spend a lot of time moving things that are just zeros and operating on them, and that's all very unnecessary. I mentioned memory bandwidth is important. This is actually just a chart from Wikipedia, but showing how high bandwidth memory, which is the main memories used in GPUs these days, have been improving. The current sort of best is HBM3, which is on some of the latest GPUs, and there's an HBM4 due next year. I'm not sure when we'll see the first GPUs with HBM4. Generation to generation, bandwidth's improving, what's that, 30 to 40%, something like that. So it doesn't leap, it doesn't double with each generation. It's quite hard to increase memory bandwidth, but it is increasing quite a lot. And you can see the capacities will be increasing as well, how big these things are getting. So we can have more and more, bigger and bigger, now up to 64 gigabytes for one of these things with a lot of memory bandwidth. So that's going to keep growing. Of course, it's not just GPUs that could use that. So there's at least one Intel x86 CPU that's been using high bandwidth memory, and there have been others that have been planned. So CPUs could do this too, and also the sort of more application-specific processors can use high bandwidth memory as well. So that will keep going up. I mentioned application-specific architectures. So here's one that you'll have heard of, Google's TPUs, tensor processing units. This is the latest one of those, trillion V6, and they're designed to be built into these big systems so they can do training of large language models across a whole one of these things. It's quite an interesting dynamic in the market because you can't buy these. You can rent time on them, but if you wanted one right here, you couldn't buy it and have your own. So it's interesting to see how this will affect the market overall in the future. Most of the big hyperscalers are doing similar things. I've just put the Google one up. There are independent companies doing similar things. So this is one you may have heard of, GraphCore. I've put them up because they're also from Bristol. This is some former colleagues of mine from different companies in here. Most of these architectures, they have lots in common. So it's generally a big chip. They have lots of parallelism, so they can do lots of things at once. Usually lots of memory on the chip as well, which is an efficient way of doing things. And they're usually designed to be connected up in large numbers so you can process large systems. And GraphCore is another one that can do all of that. GraphCore is now owned by SoftBank, who also own most of ARM still, interestingly. SoftBank, very interesting company. You've probably heard of Cerebrus as well. The interesting thing about this one is it's a wafer scale processor. So that's one giant piece of silicon. It's a whole silicon wafer, chopped just with the sort of curved edges chopped off. This is one of their own pictures. They've included a sort of, for relative size, picture of a big GPU chip. And you just leave them all joined together, basically. And it's a way of getting more and more processors and transistors into one big, this will be about this big chip. And they've got some really quite impressive results with this approach. It's quite an expensive approach, but then in AI at the moment, what isn't? So they're kind of pitching to their market right now. And it is quite innovative. It's very interesting. And they can run lots of sort of standard AI software. So this is some interesting stuff to watch, but it's not cheap. So where does all that leave us? Well, I think we're going to see probably greater divergence between what we're going to get, which is really what's being driven by AI, and maybe what we would have chosen for HPC hardware. But this is almost our modus operandi, right? In the high-performance computing space, this is kind of what we're used to. AI is the latest thing to do this, but it's not the first, and it won't be the last. So this is just kind of what we're used to. we're going to have to be flexible and adaptable again, I think, and figure out the best ways to use this hardware. And there is lots of work that already does this. So there's lots of work looking at, can we use the lower precision? Can we leverage things like TensorCores for things that aren't maybe what they're originally intended for? So we're kind of used to this. In the past, occasionally we have jumped ship, haven't we? So maybe we used this sort of big iron type HPC in the 1990s, and then when the kind of Linux cluster came along, we kind of figured out how we could jump across to that and adapt. They were very non-ideal at the time. So if you remember in the very early days, x86 was only 32-bit. It was very flaky, so it didn't have things like error correcting codes. It often didn't have floating point hardware, so floating point was quite slow, it was in software. And then over time, all of those things improved. But in the very early days, they kind of sucked for HPC, but they were on a really fast trajectory of improvement. And so it was a disruptive thing to jump across to. It's not obvious what the alternative would be today, is it? There's nothing that you could say, actually, if GPUs aren't going to be what we really want now for HPC, because they're becoming too AI specific, what could we use instead? We've got really fast processors in our phones, but those aren't easy to get and turn into a cluster or something else. Raspberry Pis are quite weak. Will there be anything for RISC-V, something else? We don't know. There's no obvious contender. But it's worth keeping your eyes open just to see if anything does come out at some point. When markets become very extreme, they tend to create something new. So maybe that will happen at some point. It's not obvious that it will, but it might. And in fact, we're already seeing CPUs starting to pick up the best bits, the greatest hits of GPUs. So I think like TensorCores, etc., are now starting to be integrated back into a CPU. And as GPUs, the supply and demand tips more and more into making them such hot commodities, and they're so expensive, it might be that you can get more done for your dollar on CPUs again. So it's worth keeping your eye on that and seeing what happens over time. In my research group in Bristol, we've wanted to play with all this computer architecture stuff for a while. So rather than just observing it, we wanted to be actively involved in research. We've developed this really cool piece of software called the Simulation Engine, or SimEng. It lets you build models, very detailed models of processor architectures, and play around with all sorts of things. So I asked a crazy question to my group: how wide could a processor get and it still be useful? We've had a model of a 64-way superscalar processor to see what happened. It was actually quite interesting. So you can ask interesting research questions about architectures and now get decent answers. So the Simulation Engine, it's all open source. You can download it and try it. It's being used with some of our research partners. There's some work that's going on with ARM, with Recon. Recon are using it to look at some ideas for the next Fugaku supercomputer. SciPerl in Europe are using it as part of the European Processor Initiative. We've got models in SimEng for things like, the first one we did was the Marvell Thunder X2. It's a bit old now, but that's what we built the first Isambard supercomputer from. And then since then, we've done a Fujitsu A64FX. That's quite an exotic beast. That was a good test to see if we could model that accurately. We've got a model of an Apple ARM Firestorm core. So that's it. My first one of these ARM-based MacBooks was an M1 based, and we've got a model of that. We've now got a model of an ARM Neoverse V2, which is the core in the Grace Hopper, the Grace CPU, and also in the Amazon Graviton 4. We've also got a model of a sort of generic RISC-V, and you can take any of those and you can kind of easily change them to almost anything you like, and then do all sorts of interesting research with it. So we're actually doing some AI-driven microarchitecture studies now, so searching the design space of, if we want a processor that's good at this sort of thing, what would it look like? Would it actually be wide or narrow? Could it have lots of vector units? How wide should they be? Well, we can, rather than just sort of guess now, we can actually do a sort of AI-based search of the design space using SimEng. And there's all sorts of interesting things we're using that for. So just to bring all of that together, what I think I've said. Well, I think the AI market, however big it is, it's huge. It's kind of bigger than everything else at the moment. That will, for some years, I think, continue to drive computer architecture space. That's just a matter of fact. It won't be forever, but it will be for a while yet. Essentially, we need to adapt or die again. We've done this before, and we'll do it again. But I think that's just the way it's going to be. It means we need to get good at using GPUs, lower precision floating point, TensorCores, smaller memories. So rather than having hundreds of gigabytes, we've got 100 gigabytes, but with lots of memory bandwidth. It's not clear we've got much choice at the moment. I'm kind of interested if we do. CPUs are actually pretty interesting again. They're absorbing lots of the best bits of GPU, so keep your eyes open there, see what you can do. And in general, we're going to keep seeing more and more cores. They're going to get wider and wider pipelines. They'll have more and more accelerators, things like TensorCores and other things will keep being added. The bandwidth will keep going up. You'll see multi-chiplet devices. So AMD's been doing that for a while, but I think everyone's going to go that way over time. It just makes sense. Chip can only be so big, but that doesn't mean you can't put multiple of them down in a big package. That's going to be the way that will go. And right now, it means everything keeps getting more and more expensive. And that's different to what we were used to in the past, where it might have been the cost stayed the same, but you got more for your money. Now that's not so clear each time. Again, that might not always be the case, but it's certainly been the case for a few years, and it will stay the case for a bit longer, I think. So that's what I think is going on in computer architecture in general. I've got a brilliant team of people in Bristol, in the HPC research group that does all this simulator work, and in the Bristol Centre for Supercomputing team who are building these. We built 2 supercomputers in the last year, and we're about to do another one with a small team of people, and we're building the whole site from scratch, it's a remarkable achievement, and it's all down to the people at the end of the day, isn't it? With all of these things, it all comes down to having really good people. So I'm very lucky to work with lots of great people in Bristol, which is almost as far away from here as you can possibly get. So the first time I've been into the Southern Hemisphere, and it's been really amazing so far. I'm so glad that I've come down. So that's everything I had to say. Thank you very much.
Thank you very much.